Could waste plastic become a useful fuel source? Plastic waste dumps, says Professor Erwin Reisner, could be the oil fields of the future. And effectively, plastic is another form of fossil fuel, and says Professor Reisner, who is Professor of Energy and Sustainability at the University of Cambridge. And it's rich in energy and in chemical composition, which we want to unlock, and but the chemical bonds that make up plastics are made to last, and of the 7 billion tons ever created, less than 10% has been recycled. Dilyana Mihailova, plastics program manager for the Ellen MacArthur Foundation, says, and our extractive, take-make waste economy means billions of dollars worth of valuable materials are lost. And worldwide, more than 400 million tons of plastic is produced every year, roughly the same weight as all of humanity. Today, around 85% ends up in landfill or is lost to the environment, where it will stay for hundreds, perhaps thousands, of years. Now the race is on to find the best way to break those chemical bonds and reclaim the Earth's precious resources locked into plastic. Mechanical recycling, where waste plastic is washed, shredded, melted and reformed, degrades plastic over time and can result in inconsistent quality products. The plastics industry is keen on chemical recycling, where additives are used to alter the chemical structure of waste plastic, turning it back into substances that can be used as raw materials, perhaps for making fuel, like petrol and diesel. But that approach is currently costly and inefficient and has been criticized by environmental groups. And so, and says Ms. Mihailova, and just as we can't recycle our way out of the plastics pollution crisis, we can't rely on plastics to fuel processes to solve the problem either. And speech now. Could a new solar-powered system show the way forward? Professor Reisner and his team have developed a process that can convert not one, but two waste streams, plastic and CO2, into two chemical products at the same time, all powered by sunlight. The technology transforms CO2 and plastic into syngas, the key component of sustainable fuels such as hydrogen. It also produces glycolic acid, which is widely used in the cosmetics industry. The system works by integrating catalysts, chemical compounds which accelerate the chemical reaction, into a light absorber. And our process works at room temperature and room pressure, and he says. And reactions run automatically when you expose it to sunlight. You don't need anything else. And assures Professor Reisner, the process produces no harmful waste. And the chemistry is clean, and he says. Other solar-powered technologies hold promise for tackling plastic pollution and CO2 conversion, but this is the first time they have been combined in a single process. And combining the two means we add value to the process, and says Professor Reisner. And we now have 4 value streams: the mitigation of plastic waste, the mitigation of CO2, and the production of 2 valuable chemicals. We hope this will bring us close to commercialization. And in addition, Professor Reisner says his system can handle otherwise unrecyclable plastic waste. And usually, plastic contaminated with food waste goes to incineration, but this plastic is really good for us. In fact, Food is a good substrate, so it makes our process work better. And researchers around the world are looking for ways to turn unwanted plastic into something useful. When broken down, the elements of plastic can be remade into a myriad of new products including detergents, lubricants, paints and solvents, and biodegradable compounds for use in biomedical applications. Nature has found ways of breaking down polymers, substances made up of very large molecules, and plastic is a synthetic polymer. Nature has found ways of breaking down polymers, substances made up of very large molecules, and plastic is a synthetic polymer. And there are already bacteria out there that have enzymes designed to break polymers down, and says Dr. Victoria Bemmer, Senior Research Fellow at the University of Portsmouth. And we can tweak these enzymes by changing the structure of them very slightly, to make them go faster, make them more firm or stable, and using machine learning, drive. Bemmer and her team have developed variants of enzymes adapted to deconstruct all varieties of polyethylene terephthalate, PET, a type of polyester. The enzymes break the plastic down in a similar way to chemical recycling, says Dr. Bemmer, but because they are akin to enzymes found in nature, the process can be done in much more benign conditions and where chemical recycling uses chemicals, the Portsmouth University team are able to use water. And the highest temperature they need is 70 C, meaning energy consumption can be kept low compared to other processes. Dr. Bemmer and her team are developing their enzymes further and hope that their work will help them create a sustainable circular economy for plastic-based clothing too. Polyester, made from PET, is the most widely used clothing fiber in the world. However, recycling synthetic fabrics using enzymes is not easy. The addition of dyes and other chemical treatments make it difficult for them to be degraded in a natural process. And polyester is an absolute pain, and says Dr. Bemmer. And plus, it's very rarely just pure polyester. You find mixed fibers as well. And the team hope their enzymes will reduce the PET in waste textiles to a soup of simple building blocks, ready to be made back into new polyesters. And we're at a very early stage, and says Dr. Bemmer. And we don't know yet if the dyes and additives to these fabrics will inhibit the action of the enzymes on the polyester chain. Hopefully they won't have an impact and we can just carry on, but if they do, we can develop our enzymes further. And worldwide production of plastic continues to increase, and is expected to triple by 2060. For many, recycling remains the focus in addressing the issue, but some argue this will never be enough. Back in Cambridge, Professor Reisner's team are taking baby steps in the direction of commercialization. They plan to develop the system over the next 5 years to produce more complex products and hope that one day the technique could be used to develop an entirely solar-powered recycling plant. Around 600 million tons of syngas is already produced every year, says Professor Reisner, but it's largely from fossil fuels. And if we can make syngas, we can access almost all of the petrochemical industry and make it sustainable. And